So Dr. Randy Kyung is a visionary quantum physicist, inventor, and entrepreneur who has dedicated his career to bridging quantum mechanics, cryptography, and artificial intelligence. With a PhD in physics, his pioneering work has earned global recognition, including a NASA honor for his early research on electron capture cross-sections. As a co-founder and the chief scientist of Quantropy Inc., Dr. Kyung drives the development of the next generation quantum secure technologies. He holds over 40 US patents across telecommunications, cybersecurity, and authentication. His most notable inventions include the first two-level authentication patent, which helped lay the foundation for the FIDO security standard. Dr. Kyung is also the creator of several breakthroughs innovation, like the quantum permutation pad, QPP, homomorphic polynomial public key, HPPK, cryptography, quantum permutation pad with random number generator, a true random number generator based on quantum principles, quantum encryption in phase space, QEPS for coherent optical security. Crowning these contributions is his quantum cryptographic dynamics, QCD, framework, a unifying model that supports a complete post-quantum cryptographic ecosystem. Through this work, Dr. Kyung has proposed a quantum secure eco-crypto system architecture, paving the way for resilient cryptography in the era of quantum AI. So, Dr. Randy, the floor is yours.
Okay, thanks very much. So, I can share my screen. Windows. Okay, can you see my screen? Hello?
Yes. Yes.
Okay. So everybody can hear me, right?
Yes.
Yes.
Okay. First, thanks, Taha, that gave me this opportunity to this initial talk. So my talk is virtual quantum reality, a new paradigm for true uniform random number generation. So I'm Dr. Randy Kwong, co-founder and chief scientist of Quantropy. So what is VQR? Basically, VQR is just a conceptual topic. It can be extended for cryptography and security, quantum-inspired computation, quantum simulation and modeling, and also quantum AI, machine learning integration. Or you can, expand to this just a few list. So. For the VQR, we want to get a true uniform randomness. So the question is, can randomness produced in software be truly unpredictable? That is a big challenge. We knew this, for example, here at least 3 randomness source, coin flip, this physical randomness. In the past half century, or more than half century, we knew the possibility is 50 to 50, hit and tell. But recently, experiments show this 50.8 to 49.2 possibility. So they're not even, it is unpredictable, but they are not uniform distributed. Of course, we knew this pseudo random generator. We have a bunch of these PRNGs. It is a deterministic algorithm and based on a seed. So all this randomness is reproducible. So once you know the seeds, you know everything. Of course, today we have many QRNG, quantum random number generator, based on quantum uncertainty. Of course, the randomness is true, but the output is not usually uniform. They are biased. So QRNG must follow by a post-processing, also we call whitening algorithm. So VQR for true uniform random number generation, we want to leverage both PRNG and quantum property. So why this true random does matter? Of course, cryptography, we need keys, total unpredictable, nonce. For example, for AES encryption, we need this unpredictable nonce, sorts for IV. All this, we need truly random. If the randomness is not truly, security can be collapsed, Of course, for machine learning, AI, Monte Carlo simulation, all this, the high quality PRNG should be enough. But if you want to integrate with the cryptographic, then you need the true randomness. So real world failures, once the true random is broken, basically predictable, then the securities become a trouble. So our goal is trying to get reliable, auditable, high entropy randomness and community system with all our system. This is big challenge. I should say, I never expect this before January 2025. I think this is impossible. So after New Year, I explore this entropy. So the computer system, we found this actually magic things. So basically, we call QPP-RNG is leverage both PRNG and QRNG. We want to put them together. So that is basically, you can say visually, visual quantum random reality or randomness. So in order for us to talk about this QPP-RNG, we did go back a little bit to 7-8 years ago. I think this perfect secrecy from Shannon, which published in 1948, and we know the OTP is perfect, but you can only use for one time. So the problem, why? How can we make perfect secrecy reusable? This struck me for almost 2 decades, until 2027, when I visit my, childhood village. I figure out this, OTP is based on the Boolean algebra computing, and now quantum computing is a linear algebra. So the shift from Boolean to linear actually is from number, for n-bit system numbers, the state is 2 power of n, to n-bit system quantum system. That's the 2 power of n basis, basis vector. So then you have a big jump from 2 power of n possible operation to 2 power of n factorial this many operation. That's what we call QPP. Briefly, what is a QPP? QPP is basically permutation cryptographic primitives with a 2 power of n factorial possible key or gates. The gates, like what Solomon said, this operation, but for n-bit or n-qubit system, how many this permutation gates is? 2 power of n factorial. This is well known since almost 200 years ago from Galois. So the problem is how we can use that, So after we understand this QPP can be used for cryptography, so then we extend this QPP for symmetric crypto, like OTP style, AES like block stream cipher. Then, of course, this implementation, you can go matrix implementation for classical system. You can go GITS implementation in quantum native, like Alain already did this implementation in IBM quantum computing system. So also the permutation gates can be implemented arithmetically. mathematically. So that's where we created this public key, HPP, homomorphic polynomial public key, which can be quantum safe for KEM, K encapsulation mechanism, and digital signature. So this year we accidentally found this can be extended for random number generation. So that means, crypto, we found this QPP to be a DNA for cryptography. Here is a simple model, we always know array, order array, for example, 1 to number n. We have the how many permutation for this order array. You have a permutation n factorial. For example, if n equal to 4, you have 4 factorial, you have 24 permutation. If n equal to 5, you have 120 permutation. If n equal to 6, 720 permutation. So permutation space is always n factorial. The beauty is that this order array, array C, can be considered as a cipher array of order array AI through a permutation P, the P hat. So, and also we know all the permutation or gates or operators, they are unitary reversible, and it can be use a set of permutation to represent another permutation. This is where we created this random quantum permutation path, P inverse equal to this product, all this. So this basically you can randomly generate this permutation operation, then make this path to be a reverse permutation of P, so you can go to sort the system. So we knew this, actually we knew this for long time, but we thought this is stupid sorting algorithm. But stupid means entropy. So here we can, we create this, so we can repeat for sorting m time, so that we have the possibility m time n factorial become this entropy source. So this is this system that will offer you entropy equal to log base 2 m time n factorial. If you want to create an n-bit entropy source, you need this log to be much larger than n. Here is the table give you for n capital N equal to 4, then m from 1 to 4. You can see the equivalent entropy equal to from 4.58 to 6.58 bits. Okay. So a high-level view for this, a VQR system for random number generation, it consists of a permutation sorting engine, a computing system as entropy source. The two conjugated observables in the system is how many permutations used to sort this order array, and how much time it's taken to complete it. Of course, n we can consider as an operator, permutation count, okay, to complete a certain sorting cycle. Then we can reduce use the mode 2 power of n to produce the number in the n-bit system. Time, this ellipse sorting time, this is a magic. For any computer system, for a given disorder array, then you try to use the same sorting path, QPP path, the time every time is different. Unbelievably, they're different. Okay, so this creates this n operator and t operator. They are conjugate of observables. You never be predicted their this two, the t. So here's a diagram to show how this QPP origin design make it work. So the system will output n, the permutation count, or modulo 2 power of n, or the permutation time modulo 2 power of n. So to be the evidence for true uniform randomness number generation, you need to have these three items. First, the uniform output for each number from 0 to the power of n minus 1 should be appear to theoretically identical probability. In practice, they're not exactly the same, but they have a fluctuation. Then the normal distribution, the frequency of a symbol over many trials, or the symbol count cluster around the mean. So you can see the diagram at the bottom. The left side they will show averagely they are around the average, so they have fluctuation. Then the fluctuation, the count, if you do this Bell, this called Bell graph, you will see a normal distribution. So then there's a theorem called central limit theorem. If this is a distribution, normalized distribution for the sample count following the standard normal distribution, then this each symbol's distribution is uniform. We will say this later on. So this is a diagram I did the calculation, did this sorting with the 4 elements. The disorder is 3, 0, 1, 2. So we're trying to sort it back to 0, 1, 2, 3. So you can see here, this is for 1 million times sorting. 1 million times sorting, with each sorting we repeat 4 times. So this you can see on the left hand side, the permutation count distribution is skewed, right skewed distribution with a long tails. They are not uniformly. At the bottom, left bottom is the time taken is also similar right skewed distribution with a long tail. However, if we do the projection to computational base for n bits computational base, you can find that they are become some certain uniform distribution. So for this, we take this, consider this as 4 bits random number generation. So you can see they produce this from 0 to 15, 16 samples. Each sample accumulated almost 32,000 times. So this make up mean, So you can see top and bottom on the right hand side, we call this reduced distribution, looks almost uniform. So here I can show you on certain principle we discovered, in this system. For a given quantum permutation path, 2BP path 1 to 10, for each given path, we repeat many times. Here at least 10 times. You can see the permutation count is the same, but the permutation time always changing. Always changing. That is the beauty. We never saw this in the classical system. So here we want to show you how this system converges into a uniform distribution. With n 4 elements array, repetition time m lowercase m equal to 1. You can see this Bayer graph. They have a standard deviation sigma over 1,000 for the n. And on the right hand side for the time t, over 2,000. So there's a lot normal distribution because the sigma is too large. If we increase for the same given disorder array, increase the repetition time to 2, the squeeze condensed to the central position. For averagely speaking, there are 3,900 frequency. On the left hand side, the standard deviation reduced to 115. On the right-hand side, for the time, reduced to 3080, the standard deviation. Once we continue to increase the repetition M to 3, on the right-hand side for the permutation count, you see this the standard deviation, reduced to 64.3, and on the right-hand side, reduced to 72. They're almost close to the standard deviation, standard distribution. Let's further we get the M equal to 4. Both time, sorting time and sorting permutation count, they coincidentally going to converge standard distribution. Once this becomes a standard distribution, then the sample value from 0 to 15 become uniform. Okay, that is a central limit theorem. So here is a table to show you what's the standard deviation for the top part of this table. You can see when n from 1 to 4, the standard deviation is going downstream to the theoretical one. Theoretical should be 62.38. They're very close, very close. And to prove your random number generation to be, truly identical independent device IID, that's at least the standard. You also need to measure the entropy and the chi-square, the very critical chi-square. So you can say for 8 bits, when m equal to 1, you see the entropy is 7.9. Then m equal to 2, they raise to 7.9993. And for same thing for n, for the permutation count and for permutation time. And chi-square, the ideal theoretical value is 255, but the practical will continue to close to 255. So this is a experiment to show, to demonstrate this QPB RNG converging to uniform predictable random generation. So once we prove that, so we can now merge this two distribution to one. So using the PRNG to generate permutation path. However, the PRNG will be driven by the system jitter, the permutation time. So now they can self uniformly generates the random number output the delta n. So we recently published a paper in the scientific reports. Reports across all of this major platform, Mac OS M1, Mac OS Intel, Windows 11 with Intel, and Raspberry Pi. They show almost similar, pass the least standardization requirement for the minimum entropy. We reach sample A7. Compare with the commercial RNG like ID Quantis, the most popular one, Quantis. So our minimum entropy is almost identical with this QRNG. However, we achieve this in the normal, ordinary computing system. So one more thing is we have did this benchmark for mobile, iOS, and Android, demonstrates similar behavior. So we can enable all this computing device to be truly uniform random generator without require extra spatial hardware. And we also did this in the IoT device ST Micro. Of course, they're slower, but has similar behavior. So in conclusion, virtual quantum reality for truly uniform random generator offer programmatic auditable path to true uniform randomness on any computing system. So this QPP RNG demonstrates how quantum inspired solution plus physical system physical jitter because all this integrated jitters across the system architecture and the operating system, scheduling, everything integrated together produce high quality entropy. So anybody if want to try this, we can discuss after the this session, or you can reach me through my email. You can get contact me from my LinkedIn. We can have a more discussion. Thanks very much. This is my presentation.
Thanks very much, Dr. Andy. So it's a very excellent talk and a very excellent presentation indeed. And thanks for highlighting the role of virtual quantum reality and also the awesome portability of quantum permutation pad with random number generator, and also how this is really portable on different hardware. So the question now, are you gonna, for example, do you have a vision to like commercialize this as a product or as a software, or what do you envision?
Thank you very much. Of course, we already implemented this in our product. So basically, we already made a demonstration over this STMicro seminar. Because this is, we're looking for this unpredictable, so without extra cost. So this is very interesting. Think about it. Have one more minute I can talk about so in the past century we look for the cryptography. The cryptography itself is open. You always have the symmetric like AES rely on this. Unpredictable true random key. Then where you get this key, use public key to distribute this. The public key is broken. Then you have to create a PQC cryptosystem. Then once we face the PQC cryptography, we forgot where we get the true random. So that's how we need the QRNG, we need TRNG. Think about how you integrate this QRNG, TRNG into your cell phone, into your system. This have a scalability. Basically, from piece to piece, they're opened. So cryptography, they have three pillars: symmetric encryption, public key, a random number. These three, there are a lot of complete system, like an ecosystem. Every broken piece, like if you use a Kyber, all the random number is PRNG. Okay, if you do QRNG, now you have trouble how to put the QRNG with Kyber. You cannot basically. This is a problem in the system broken. So whenever a system broken, there is a weakness of the system security, right? So we try to create a ecosystem. We build this into the public key, then into the symmetric key. So there's kind of self-closed system. I think this is important.
Yeah, definitely. Yeah, thanks for this impressive. I'm pretty sure it's like an impressive product, and also we'll be looking forward to try and also test it in the near future.
Yeah.
So thanks very much.